Hey everybody, welcome to our new unit. So we're not actually going to start our new unit today. We are going to practice a new skill that will help us in this upcoming unit. So what we're going to learn today is we're going to learn about graphing. Okay, so we're going to learn a new way to do graphical analysis. And although many people hate analyzing graphs, it's a very, very important part of Physics 20 and 30. And lots of the skills that we learn from this lesson will be very, very helpful in Physics 30 when we're actually back in school. So this is what we use in high school. The most basic useful graph is a linear one, and it uses y equals mx plus b. So you have to remember that m is equal to the slope, and then b is your y-intercept, right? So if you have a graph, right, this would be your b. That would be your y-intercept like that. And y and x, for our purposes, so our x value is going to be our manipulated variable, manipulated, and then our y value is going to be our responding variable. Okay. So that's how we're going to use it. It's a little bit different in math. You've done this in math, but it's a little bit different in science. Okay, so the term that's going to come up quite a bit in physics is the term proportional. Proportional, which has this little symbol like a fish. If you change one number, what happens to the other number? So let me give you the 6 possible situations that we're going to see. So two numbers can be directly proportional, inversely proportional, squared proportional, inverse squared proportional, square root proportional, and inverse square root proportional, which it's all kind of the same stuff, and you'll get the hang of it. It's not like you have to memorize 6 different things, but those are the 6 different scenarios that you're going to see. Okay, so from those 6 scenarios, I'm going to give you 4 examples. So our first example is we can have v equals d over t. So when we have v equals d over t, the two numbers that are directly proportional are distance and speed. So you can tell that they're directly proportional because they're on this, when they're on the opposite side of the equal sign, they're both on top. V is on top and d is on top, right? So what that means is that if I increase my distance, then I increase my velocity, right? So let me give you an example. So I used to drive from Sherwood Park to Vegreville every single day. That's where I used to work. I used to work in Vegreville before working in this school. So to drive from Sherwood Park to Vegreville took me about an hour, right? And then the distance from Sherwood Park to Vegreville is about 100 kilometers. So on average, I drove about 100 kilometers per hour on average, right? That's not what I actually drove because I drove through residential areas, I drove on the highway, but that would be my average speed. So let's say we want to increase our distance. Let's say instead of going from Sherwood Park to Vegreville, I want to go Sherwood Park to Vermilion. And Vermilion is about another 100 kilometers away. But let's say I want to do that same distance or that double the distance. I still want to do it in 1 hour. I don't want to wake up any earlier. Well, what am I going to have to do? Well, I'm going to have to drive 200 kilometers per hour, right? So when we increase our distance while keeping time the same, it's a controlled variable, our speed increases, right? So that's an example. So they have a direct relationship. One goes up, the other one goes up. So if we want to look at an inverse relationship, we can look at the same formula. We can look at v equals d over t, but the two variables that have an inverse relationship are velocity and time. And the reason that I can tell they have an inverse relationship is because velocity is on the top and time is on the bottom when they're on the opposite side of the equal sign, right? I couldn't look at distance and time the way they are right now because they're on the same side. I have to move t over, and they have a direct relationship. So if I move t up here, I'd say, okay, these two have a direct relationship. So make sure you're always looking at them on the opposite side of the equal sign. So velocity and time have a inverse relationship. One's on top, one's on the bottom. Okay, so let's use the same scenario. So Sherwood Park to Vegreville is 100 kilometers away. But let's say I woke up a little bit early one day and I wanted to get out of the house. And instead of getting there in 1 hour, well, now I have 2 hours. So if I want to get there in 2 hours, logically you think, oh, well, I'm going to go half the speed, right? And that's correct, because if we increase our time, then we decrease our velocities. One goes up, the other one goes down, and that's what an inverse relationship has. Okay, an inverse squared relationship, we haven't really dealt with anything with an inverse squared relationship, but if you look at formulas on your formula sheet, you'll find them. This is an example of one that we'll use in our next unit that has an inverse squared relationship. And the two that are inverse squared are G and R, right? One's on the top, one's on the bottom. So it's inverse and R is squared, so it has an inverse squared relationship. So the same thing is going to happen if we increase our R, we're going to decrease our G. But it just increases and decreases, not doubles, halves. It does at a different amount, right? So we can use the skills that we learned in our last unit to find how it would affect it. So if I, let's say, doubled my radius, well, what effect would that have on my G? Well, I would 2, because the R is squared, I have to square that. I'm making no changes to the top. And on the bottom, I'm changing it by 4, so my G would change by 1 over 4. So when I double my radius, I quarter my G. As opposed to this one, if let me write it out again. If I double my time, well, I'm doing nothing to the top and going 2 on the bottom, then I half my speed, right? So it just increases by more. Okay, and then one more that we're going to use in the next few lessons that has a square root relationship is t equals 2 pi square root L over G. And you can see that L and T, they're on the opposite side of the equal sign. They have a square root relationship. They still have a direct relationship. So if I increase my L, I'm going to increase my T. But if I write it out like that, and I double my L, well, that 2 gets square rooted because L is square rooted. So this side I'm changing by square root 2. So my T would increase by square root 2 as well. So that's what these terms proportional. If I change one, what happens to the other one? Does it go up? Does it go down? And that's what we need to look at going forward. Okay, so we're going to practice graphing some different things. And we're going to do this graph here. So this is an EK versus M. So they give us our manipulated variable, and they give us our responding variable. So our manipulated is going to go in the X. So my M is going to go down here, and my mass is in kilograms. And my responding is my EK, and EK we know is in joules. So we're going to title this EK versus M. We always go Y versus X. So looking at this formula that's given here, we should be familiar with this formula. If we look at EK and M, we see they have a direct relationship. EK is on top, M is on top. M isn't squared or anything like that. V is squared, but M isn't. So they have a direct relationship. So as my mass goes up, my EK should go up as well. So if we want to find a scale for EK, we can just go 10, 20, 30, 40. And then for my mass, I got to go up to 60. So I just go 10, 20, 30, 40. Oops. Sorry, I ran out of room. That's not going to work. So I'll just have to go up by tens. So 10, 20, 30, 40, 50, 60, 70, 80, like that. Okay, and we graph this out. My EK is 10, my mass is 15. My EK is 20, my mass is 32. My EK is 35, my mass is 55, and then my EK is 41. We can just go a little bit above, and then we have 62, like that. Now, when we look at this data, 4 data points isn't great, but from the data that we have, we can see this makes a pretty straight line. I can't use a ruler. You should use a ruler when drawing a line of best fit, but I'm using my smartboard right now, so I can't use the ruler. So we can see that EK versus M makes a straight line graph. So that's easy. We've known how to do that for a while. But what we haven't known how to do is we need to find information from the slope. So I'm going to pick 2 data points to use. So not a great graph. I'll probably use this as my point 1 because it looks about halfway for both. And then I will use maybe this one as my point number 2 because it looks about halfway from that. Okay, so I'm going to find my slope with this line. So my y2 is 30. So y2 minus y1 over x2 minus x1. So my y2 is 30 and my y1 is 5, and those are both joules. And my x2 is 45 kilograms, and then my x1 is 5 kilograms. Sorry, I just had to write that down, and I'll switch over to the whiteboard screen. There it is. So I have that written down there like that. Okay, so make sure you put those units behind, and when I calculate my slope, I get 30 minus 5 divided by 40, and I get 0.625 joules per kilogram. Cool. So that's my slope. What do we do with that? Well, this is this new technique that I'm going to show you. So our formula is EK equals 1/2 mv squared. And what we want to do is we want to get this formula into y equals mx plus b form. And when something is in y equals mx plus b form, you have to make sure that your y value is isolated, right? So on our graph was an EK versus m graph. So EK is our y value. And in the formula, our y value is isolated. So this formula is already in y equals mx plus b form. Okay. Another thing is 1/2 times m times v squared. They're all multiplied by each other. So what that means is that I'm adding on 0 to this, right? So this isn't going to have a b because my b ends up being 0. So what I usually call this, and what we do mostly when we're starting off in Physics 20, is this is y equals mx because nothing is being added on to it. Okay, so now I know it's in y equals mx form. All that I do is I say in my graph, my y value is EK, right? Remember that my y value is EK. And my x value was mass. So my slope is going to be equal to everything I didn't circle. So I didn't circle 1/2, and I didn't circle v squared. So my slope is equal to 1/2 v squared. And if I want to find my speed that was happening for this experiment, well, I just have to move the 2 up top and then square root it. So I get that 2 times 0.625 joules per kilogram, all square rooted, is going to equal my speed. So if I go times 2 divided by my answer, so my speed for this experiment was 1.12 meters per second. And that's how we used our slope to find our speed, right? This doesn't look like anything here, but we are able to find our speed like that. Okay, so we're going to do a different example here. We're going to do the next example. Sorry, let me just switch screens here. Okay, so we're going to do an inverse relationship. So in this inverse relationship, we have VC, and we have 2 pi r over t. So we haven't used this formula yet, but what we want to get from this formula is that these two have an inverse relationship, right? Because VC is on top and t is on the bottom. So we're going to graph this out. So we're going to put our manipulated, which is t, down here, and VC on our y, because that's our responding variable, and label this VC versus t, this graph. Okay, so t is just time, but if you look at all these units here, right, these are ugly numbers to work with. If we move this over 2 spots, and instead of calling it this, we call it 9.6 times 10 to the negative 2, 5.3 times 10 to the negative 2, 2.7 times 10 to the negative 2, 1.7 times 10 to the negative 2, and 1.3 times 10 to the negative 2. Well, we can say that all of these are times 10 to the negative 2, and this is time in seconds, like that. But these numbers are much nicer to work with. Now we're going from 1.3 to 9.6, so we just have to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then VC is just your speed in a circle. So it's going to be meters per second. And we can just go 1, 2, 3, 4. So now we've got our graph all set up, and we can graph out this information. So when VC is 0.55, this one's 9.6. And when VC is 1, we have 5.3. When VC is 2, we're at 2.7. VC is 3, we're at 1.7. And when VC is 4, we're at 1.3. So now when we look at our data from this one, we can see, ooh, this isn't really a straight line. This is a curved line like that. And that's what our graph always looks like. Whenever you have an inverse relationship, you're always going to get a curved line graph. And we need to use slope to help us find information about this graph. So yeah, we can't find slope from a curved line. So what we need to do is we need to straighten this out. So I have to erase everything here because I need to use my graph again. So I'm just going to erase everything. So to straighten out a graph, I get this question all the time. How do I straighten out the graph? You need to make it look like it does in the formula. So in the formula, I'm just going to add a 1. This is what t looks like on this side of the formula. It's 1 over t. And in the formula, VC, well, it just looks like it's by itself on top. So VC is okay the way that it is, but t needs to be 1 over it. So I'm going to go 1 over t. So my units before were seconds, and whatever we do to our value of t, we also do our units. So our units become 1 over seconds. So what I'm going to do is I'm going to grab out my calculator, and I'm going to take all of my t values, and I'm going to 1 over them. So just give me a second for that calculator to open up. Okay. So I'm going to go 0.096, or I can go 1 over 0.096, and I get my answer to be 10.4. So I can write 10.4 on there. Right? And a quicker way of doing that is instead of 1 overing it, if you go 0.053 and then you type this button right here, x to the negative 1, it inverses it as well. So I end up getting 18.9. And then I go 0.027 and I 1 over that, and I get 37.0, 0.017, I 1 over that, I get 58.8, and my last one 0.013, I 1 over that, and I get 76.9. Okay, so now we have these values that are 1 over it. So VC was fine, it's by itself, so VC stays like this in meters per second. And this is a VC versus VC versus graph. So our values that we're graphing out now are not t anymore, they're 1 over t with the units of 1 over second. So this isn't a VC versus t, this is a VC versus 1 over t graph. Our last one was VC versus t. So for our scale, we can keep our y the same, and we need to go up to 70, 77-ish. So if I just go up by tens, that's good enough. That'll use most of our graph. Okay, now I'm going to graph out this information. So at 0.55, we're at 10.4. At 1, we're at 18.9. At 2, we're at 37. 3, we're at 58.8. And 4, we're at 76.9. Like that. And now, when you look at our data, we get really nice straight line data, and that's because we straightened out our graph. So with your ruler, you draw on a line of best fit, and I can't use the ruler again, so I'm kind of hooped with that. And then I'm going to select 2 points, and we're going to find our slope. So I'm going to select this point as my point number 2, and then this is close enough for the bad graph that we have as point number 1, and I'm going to use those 2 points, and I'm going to calculate my slope with that. So just let me write these values down, and then I'll switch the screen. So y2 looks to be about 3.75 meters per second. And then y1 looks to be 0.5 meters per second. x2 is 71 over seconds. And then x1 is 10 1 over seconds. Okay, so let me switch screens. I've got that written down. So 3.75 minus 0.5. Divided by 70 minus 10, and I get 0.5416 repeated. Now the units for this one are a little bit tricky, and the way that I do these units is I just draw a line. So we start off with meters per second. So for the top one, I start on the top, and then the bottom one, I start on the bottom. So we have 1 over seconds. So what you need to know is anytime you have, I can add a 1 here, it doesn't change anything. Anytime I have 1 over seconds, it's the same thing as having 1 over 4. Well, it just becomes 4, right? Because if you go 1 divided by 1 over 4, or I could call that 1 over 1 divided by 1 over 4, it's the same thing as multiplying the reciprocal. And if I multiplied the reciprocal, I'd get 4. 4 times 1, 1 over 1, like that. So instead of writing 1 over seconds, I can cancel that out and move my seconds up top. And now I have a seconds up top and a seconds on the bottom, so those cancel out. So my units just become meters. Okay, and now the formula that they gave us VC equals 2 pi r over t. And our graph was VC versus 1 over t. So to get this formula in y equals mx plus b form, we have to make sure that our y value, which is VC, is isolated, which it is. So it's y equals mx. And there's nothing added onto it, so it's just a y equals mx. Okay, so now our y value is VC. Our x value is 1 over t, and I can add a 1 here. Adding a 1 anywhere doesn't change it. So x equals 1 over t. So my slope is equal to anything that I didn't circle. So my slope is equal to 2 pi r. So what we can do is we can find the radius of this circle by just moving 2 pi down below and using the slope that we found here. So 0.5416 meters divided by 2 pi. So 0.5416 repeated divided by 2 pi. Oops, what I didn't do, I didn't put brackets on the bottom. So we get 0.086 or 8.6, that's meters, or 8.6 centimeters. And that's how we get our radius from that. Okay, so I am, let's do one more. Oh, sorry, I missed this one. So this is what I usually do as a board question. So what I want you to do is I want you to try this question as a board question. If you have the notes, I gave you the notes yesterday. Print off the notes so you have the graph paper and you can test this out. And I want you to see if you can graph it out, get a curved graph, and then straighten out your information based on this formula, and then see if you can tell me what slope is equal to. So pause the video, try that on your own, and then I'll go through it so you can tell me if you can figure out what slope is equal to. So when I say what slope is equal to, I'm just talking about when I said like slope here is equal to 2 pi r. See if you can get to that step on your own. I know this is a formula we haven't used before, and there's some stuff in here we haven't used before. So see if you can get to that step. So pause it, and now I'm going to go through it. Okay, so I will make a G versus R graph, and this is G, which is in meters per second squared, and R is in meters. And I should have said that before when I was telling you stuff. But yes, it's the regular G value that we're used to. We go up to 8. So 2, 4, 6, 8. Then our R value will move over 2 spots. So it's not going to be meters, it's going to be times 10 to the negative 2 meters, like that. Okay. And we got to go up to 16, so if we just go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, this is 0 down here, then we'll have enough room. So 2 and 16.3, 4 and 11.5, 6 and 9.4, and 8 and 8.1. Right, so you can see that we don't get a curved line, we don't get a straight line, we get a curved line when we do this. So it looks super similar to the graph that we had before. So now I'm going to straighten out my data. Okay, so to straighten it out, we need to make it look like it does in the formula. So G looks okay the way that it is. I'm just going to add a 1. And then in the formula, all the R's are 1 overed and they're squared. So I need to take all of my 1 over, I need to take my R's, I need to 1 over them, and I need to square them. So remember that this was meters per second squared, this was meters, so my units become 1 over meters squared. That's going to be my new graph. So I'll open up my calculator and I'll type all those in so you can see how I do it. So I would just go 0.163 squared, and then I usually just 1 over my answer like that. So I get 37.6. And then I have 0.115, I square it, and then I 1 over it, and I get 75.6. 0.094, I square it, I 1 over it, and I get 113.2. and then 0.081, I square it, and then I 1 over it, and I get 152.4. Okay, so now I have my new values that I'm going to graph. So now I'm going to make a G in meters per second squared, and those all stay the same, versus 1 over r squared, and that's going to be in 1 over meters squared. So I get G versus 1 over r squared. That's my graph title. And I got to go up to 152, 20, 40, 60, 80, 100, 120, 140. Yeah, go by 20s. So 20, 40, 60, 80, 100, 120, 140, 160, and that's good enough. Okay, so 2 is at 37, 4 is at 75, 6 is at 113, and 8 is at 152. Like that. And you can see, oops, let me try that one again. We get nice straight line. Oops, erase my data. Sorry, 75. There we go. That's a little bit better of a line of best fit. I should be using a ruler. Hopefully you're using a ruler at home, but that's what we end up getting. So I'm going to find the slope with this line. And I don't usually like to go this far up, but this looks like the first one that I can really estimate. Ooh, this is a bad line of best fit to estimate. Maybe I won't use that one. Maybe I'll just do my best to estimate this one and this one. I'll just make them far apart because they're not great. Okay, so my y2 is 8 meters per second squared. My y1 is 1 meter per second squared. And then my x2 is, I'd say, 145, 1 over meter squared, and about 15, 1 over meter squared. Not the best points to use, but not the greatest graph either. So, yeah. So let's calculate what our slope is. So we'll go 8 minus 1 divided by 145 minus 15. Oops. I did a negative instead of a minus. And I get my slope to be equal to 0.53846. And my units, so on top I have meters per second squared, and then on the bottom I have 1 over meter squared, right? And again, we have 1 over meter squared, so I can just move the meter squared up top. And I have meters times meters squared, which makes meters cubed, all over second squared would be my units. Okay. And my graph was G versus 1 over r squared, and my formula was G equals GM all over r squared, like that. It's already in y equals mx form because my G is isolated. So I go y equals mx, my y equals g, my x equals 1 over r squared. So my slope is equal to gm, right? And what we could do from this graph is we could figure out the mass of the planet. I never asked you to do that, but we can move the g down below because that g is a constant. So if I take 0.53846 meters cubed per second squared, and I divide it by g, and this g is always 6.67 times 10 to the negative 11. We'll learn about that, and the units are Newton meters squared per kilogram squared. And we would end up getting 8.1 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. And it would end up being kilograms as units, and that's how you can find the mass of a planet if you have enough information. So yeah, that's basically what you would do. Do you want me to? I could break up these units if you want. I feel like I'm going to get a question about that. Right. So on top we have meters cubed per second squared, and on the bottom we have Newton meters squared per kilogram squared. So I can move the kilogram squared up to the top like that. And I also know with F equals ma that a Newton is equal to a kilogram meter per second squared. So instead of writing a Newton, I can write a kilogram meter per second squared, and I can move the second squared up top like that. Second squared cancels out. We have meters cubed, those will cancel out. Kilograms, and that's why we end up with kilograms. Okay, so hopefully that went okay. Yeah. So there's one last question. I'm not going to do it because I feel like this video is already long enough and you guys are probably bored watching this. I just want to take this formula and I want to show you how you would rearrange it if it wasn't already in y equals mx plus b. That's the only thing I really want to do with this. So I have vf squared equals vi squared plus 2ad. And they say that the manipulated is vf, what has to go in the x, and d is your responding variable. That's what you're measuring, right? So to isolate this, we need to isolate d, okay? So we already know how to rearrange this. So we'd minus a vi squared from both sides, which would cancel that out. So we get vf squared minus vi squared is equal to 2ad. And then we'd move the 2a down below. Okay, so that's how we would isolate d, but it's not totally in y equals mx form, right? Because when we write out, I guess this one's actually y equals mx plus b, because there's a adding and subtracting. So d is isolated, which is good. So I'm going to do that first. And vf is our x value. So I want to make sure that comes next. So here I have vf squared over 2a. And then I have minus vi squared over 2a. So this here and this here is the same thing. You can do it under everything or you can do it individually. It doesn't actually make a difference. So this is a nice way of writing it because now it's in y equals mx form, right? Because d is our y value. Our x value is vf squared. So just ignore this because this is my slope. This is my y-intercept stuff. So my slope is everything else. I can add a 1 here. My slope is equal to 1 over 2a, like that. And then this stuff over here is my y-intercept. So instead of saying minus, I'm going to go plus negative so that they're both plus. So b is my y-intercept. And this tells me that my y-intercept is equal to negative vi squared over 2a. So that's how we would do a much more complicated. And there's a little bit of homework like that. You just have to rearrange it and get it into y equals mx form. Okay. Okay. So I want to do some virtual board questions because these are questions that are asked quite a bit. So I'm going to give you a formula and then I'm going to pause a little bit and you can pause the video even if you could select A, B, C, or D as the answer of what the graph would look like. So I'm going to show you a little trick before we do this. I'm just going to get this full screen. So if you ever want to know what a inverse graph looks like, if you click on this y equals on your graph and then you go 1 divided by, and you click this button right here, x, and then you graph it out. This is one we're focused on. This tells you what an inverse graph looks like. So we never did an example with, let's say, a square root relationship. So if I want to know what a square root relationship looks like, if I just go square root, and then I select x, and I graph it out, oh, That's what a square root graph looks like. Well, what does an inverse square root graph look like? So if I go 1 over, 1 over square root x, what does that look like? Oh, cool. What does a squared relationship looks like? I just go y equals x squared. Oh, cool. That's what it looks like. So just focus on this over here. Don't focus on any other side. So it just kind of goes up like that. So you can use your graph to figure out what it looks like. So if I gave you a formula like, let's say, power equals work over time. If I gave you this formula, which we've used before, and I say that this is power and this is time. This is power, this is time, and so on. All of them is power and time like that. What would be my answer? What would my graph look like if I did a power versus time graph? Would it look like A, B, C, or D? Okay, so pause the video, figure out your answer. Okay. Power and time have an inverse relationship because power is on top, time is on the bottom. So what I want to look up is I want to look up in my calculator, well, what does an inverse relationship look like? That's what it looks like. So the one that looks closest to that would be C. That's the correct answer. Okay, so let's try another one. So what if I gave you, EP equals 1/2 k x squared. Okay, and we did EP here, and we did x squared here for all of them. So pause the video. What do you think that would look like? Would it look like A, B, C, or D? Okay, so I'm guessing most of you got this wrong, and I'm guessing that most of you picked A because you're like, okay, EP and X they have a squared relationship. So you went on your calculator and you're like, okay, what does a squared relationship look like? So y equals x squared, and that's what it would look like. But remember when we were doing these examples, right? Whenever we started off, we just graphed EP versus x. And if we graphed EP versus x, we'd get that graph. But then we straighten it out. And how do we straighten it out? Well, we make it look like it does in the formula. So EP and it's fine, but x needs to be squared. So when we did EP and then x squared, we always got a straight line graph. And that's because it looks like it does in the formula. So the answer for this is actually D, not A. Let's do one more. Okay, so I'll do one more example. So let's do, let's do the formula AC is equal to 4 pi squared R all over T squared. And let's do AC versus T. What would that look like? Okay, pause the video. Okay, it wouldn't be D. D is not the answer because it doesn't look like it does in the formula. So we need to say that, okay, AC and T have an inverse squared relationship. So we look that up and we go, we go 1 over x squared. What does that look like again? Oh, it looks like that, which looks closest to C. So we get C as the correct answer. Okay. Hopefully that makes sense. Your homework isn't in the workbook. It's the only homework that's on the workbook. So I'm gonna post homework with it, and I'll post the answers with it as well. So hopefully this goes well. And I'm gonna give you 2 days to do this. So I'm gonna give you Tuesday and Wednesday to work on this. So if you have any questions, let me know, and I can help you in any way you need. Okay, thanks for watching.